Hey, this is Kevin. I was thinking I was going to make a quick video to explain question 3 from the test. I'm going to go over the solutions and how to do it, or like the best answer is what we're looking for and that sort of thing. I guess we'll just get started. Um, so the professor posted on the website the answer key to exam 1, and you can go and download that from Dr. Newman. It's called like key 2 or whatever. The question I graded was number 3, and I'm going to explain what the question was about, what we were looking for, and just a general thought process and how you should go about solving this kind of thing. So I guess I'll just read the question first. It says, consider a situation in which a data center maintains a very large sorted file F with n elements. So let me get a paint. So some data center has a really big file F. So I'll call this file F, and it has n elements. So that's all we know so far. Data center, oh, and it's sorted. So we know all that information, and periodically F is updated by removing from it the elements of a smaller unordered file D with L elements. Okay, so now we have some smaller file here, which is called what again? D. So this is file D, and it has L elements. Did it tell me anything else? Okay, and it's unordered. So that's all I know about file D. The other thing it says is, and adding to it the elements of a smaller unordered file E with M elements. So below this we have another file, we'll call it E with M elements. Is this sorted or anything? Oh, this is unordered also. So unordered. Unordered. It's okay. So start out, the general thing that's happening is we have this large file F, it has n elements, is sorted. So the first thing you want to know when it says is large is you don't want to touch it very often because it's really large. You don't know how large it is, but in relation to the other things, it's much bigger. So in general, if possible, you just want to avoid using this file as much as you can. It'll lower your complexity of runtime, it'll lower your memory usage, and all around just much better to touch this file as little as possible. So that said, we have to remove from this large file D and add to this large file E. So basically, what you're going to get at the end is, so you're trying to create a new file here, basically, or use the same file. It doesn't matter how you do it. But in this new file, what we want to get is file F minus the stuff from file D plus the stuff from file E. So this is how it's going to work. And you don't actually have to make a new file. It's probably not that great to actually make a new file, but this is how this is like the end state, not exactly a new file. I should probably say goal file F minus file D plus file E. That's your goal. So the first thing they ask is sketch an algorithm that is more efficient than simply appending E to F and efficiently resorting for adding the elements for of E to F. So what that meant was, so get your file F here. All that was going to happen is you have to take file E and grab it and kind of just like attach it right there and then resort it. So what ends up happening when you add file F and file E together is, so let's say you got F here, now you just attach E here. This makes E a lot smaller. So F, and this is E. So now we basically attached it, and this is a naive solution to describing. So you attach them together. That's what append means. You just add to the end of it, and then you resort. But it said efficiently resorting. So let me show you some big O complexities. This is a good website called Big O Cheat Sheet, just by the way, that has the complexity for almost everything you'd use. So would recommend viewing that. So an efficient sort would be something like merge sort, quick sort too. Quick sort has a bad worst case though, so I don't know. You could have said any of these, but let's say you pick like they do a merge sort. So this is the naive solution. Oops. So in naive, we append E to F and then sort. So the complexity of the naive, well, actually, this part doesn't. You don't have to talk about the complexity yet. We'll talk about it in a minute. So the question in part A asks you to sketch an algorithm that is more efficient than doing this. So putting F to E and then resorting is very expensive just because of how large F is. So what we're going to do instead is we're going to take E. Let's see, just like take file E. The first step you're going to do is sort it. So sort using, you can use any of the sorts here. I'll just say like merge sort. Sort this using merge sort. And then this is like step one. And then step two is you merge them. Merge E and F. And that's pretty much all you have to say to get full credit. Another way of doing this is you could have done an insertion sort. It gets you less points, but you still do the appending just like this. But you put like your division line here, like for the insertion sort, like that. And you say this is like your sorted region up here, F, and your unsorted region is down here, E. Then you do your insertion sort. And that's okay, but not as nice as doing it this way. It's still better. So this is the, right here is the way you'd like to do it. Wow. So let's talk about complexities. It says analyze how much more efficient your solution is than the naive solution. So the naive was appending E to F and sorting. So let's see, sorting costs n plus m because there are n elements in F, m elements in E. If I'm correct, nm, yes, n elements in file F, m elements in file E. So go back here, sorting costs n plus m log n plus m, and that's really expensive. And I mean, it said efficiently sorting, so if you use an inefficient sort, it could be even worse with n plus m squared. But they asked you to use an efficient sort, so it's n plus m log n plus m. And yeah, so naive approach is log n plus m, n plus m. Better approach would be, so better approach is use first sort using merge sort or some sort like that, and that costs m log m. And then merging just, you have to go through both of them one time. That's all it takes. So just one pass through, so it'd be m plus n. M plus n. So the total big O is m log m plus m plus n. And you have to also identify that this is big O log n, this is big O n. So this part right here, getting this complexity of like m log m plus n, that was 1 point, and getting the big O n was 1 point. And identifying the naive solution of n plus m log n plus m was also a point. I think that gave you like the 4 points for that part of the problem. So yeah. Oh, also you have to analyze the space. So depending on the solution you used, you have to say how much bigger the file got. So this is the spatial analysis, which not too many people did actually, but it's very important. So your big O here is just the runtime, but you also have to give your spatial analysis. So like, like some kind of spatial complexity here. File F used to be size size n. Now it is size n plus m. That's all I have to say, and I get back you the last point of the question. So that is part B, and now we'll discuss part C. This one's gets a little bit. I don't want to. This one's a little bit more tricky because part C asks, sketch an algorithm for removing the elements of D and adding the elements of E that is faster than simply first removing the elements of D from F, then your solution from A. So basically, the naive solution is, we'll outline it. So say naive. 1, remove D. 2, use your solution from A. So that's the naive, and we can obviously do better. So a better solution, and there are many ways of doing this, of course, but one really good way would be to just count how many things you need to add and how many things you need to delete and do it in one pass. So let me take a look at the solutions some of the sample solutions he gave here. Okay, I really like this one. I think this is my, or actually maybe I like this one too. Actually, I like this third one the most, but all of these are valid and work. So the idea is that so let me just like write this on the side so you can talk about it. So if you remove an element, you have to shift the entire array, right? So if it's an array, you need to shift everything over. And that's really expensive. You don't want to shift everything over all the time. So ideally you like to just do one shift. So if you have to do, so you're expected, n over 2 shifts per remove. And if you're adding, how many things from D? It's like L things or something. You're adding, file D had L elements, so the total expected would be like L times n over 2 shifts. And that's a lot. You don't want to do that much. So similarly, insertion works the same way. You expect the same n over 2 shifts. So then well, actually you're just doing a solution from A, so we don't have to talk about that. But yeah, this is really expensive. You don't want to do this. So the better solution would be make a so yeah. So we're gonna make some kind of array that tells you if you're gonna insert or delete. So some kind of key value pair. You can do this with arrays. I'm just gonna say just combine D and E, and note if you're going to add or going to insert or delete. And so have a key. And so what this does for you, if you have a key value pair, is you can count up the number of like things you're adding and the number of things you're deleting. Store that as some variable. So combine D and E, count up the things you're adding, how many things you're deleting. So this tells you how much bigger the file or how much smaller the file is going to get. So let's say you have like an array here. Um, boom, 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 boom. My beautiful array right here. And we're going to say, let's say like we have to insert 2 things and we're deleting 1 thing. So in total, we're going to say it grows by 1. So since we're inserting 2 things and we're deleting 1 thing, we're going the total size by 1. So we're going to have to add like a new box at the end, basically, like this. And let me just fill this in with values so we can actually talk about it and do an actual example. Let's say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Let's say that we're deleting 1 thing is we're deleting the number 3, and let's say the 2 things we're inserting is like 2.5 and 4.5 or something. So what we're going to do is, as we pass through, we're going to start from the back and go forward. And as we do that, let me just draw this same array again. So what happens is we're going to sort this file also. So let me add another step. Sorting it makes it easier. I don't know why I switched to red, but sort DE file, because that's going to be a very small complexity. And with that, we start with the biggest one, which is 4.5. So as we make our way backwards, we start here and we keep going. Where does 4.5 like actually belong? It's supposed to go in this section right here, like between these two, between 4 and 5. That's where 4.5 belongs. So what we do is we only need 1 shift. So let me make my lines real quick. So our 1 shift happens, and 6 is put there, 5 is put there, 4.5 is put here, and then we can continue with the rest here. So what happened is I just moved this section right here to the very end, and then I put my newest one here. So that's pretty efficient. Only 1 move needed. And then we're gonna do the 1 thing we're deleting is 3, so we found 3, but we have a key that says deleted, so we can just skip 3. And then actually 2.5 belongs here. Wait, sorry, 4 goes here, and we skip 3 because we delete that. So we get 2.5, we get a 2, and we get a 1. So you might just need to like read the solution a couple times and look at it, because there's many different ways of doing it, and they're all valid. Oh, I think my roommates are raging. But yeah, so the reason this was so much better is that if we had to add and manually add every single thing and remove every single thing, it would take so many shifts that it's just not worth it. Doing it this way is a lot better, and the complexity will be, so naive solution has n plus n or L log n to locate everything. Yeah, it takes L log n if you use binary, some kind of binary search, cutting in half every time. It'll take n plus n if you do a linear search. Then n plus m log n plus m to add things and sort. This is because of the sort. You're doing an n log n sort, but it's increasing by size m. They could actually add a minus L there too if they wanted, but use like a super naive deletion where you have to like go over it every single time, which they won't do it that way. But if you did do it that way, it would be mn. But the way we could do it, take combining D, E, and E and sorting log LMN, L plus M log L plus M, which is what I did here in step 3, sort the D and E file. Then computing the values it takes N plus M time, which is actually, I did this step before, count up the number of things that you're adding and the things you're deleting. And using a Q would take at most OM. The merge is linear, L plus M. More complex way that requires more than one move. Per item. Takes a total of M times CL approach, but finding where F in the count takes a login search. At most line login. So I'm not sure if this is the way that I did it. The more complex way that never requires more than one move per item. I don't require more than one move per item. Takes a total of M time. The serial search. Right. It takes M time. Finding where in F account 0 takes login per search. Yeah. Okay. So you could also find like the exact index where everything happens if you do login per search, and at most M login time. So that's another complexity. But if you do it a little bit less efficiently, you can just go through it all one time. But yes. So actually, I just went through the whole thing in N plus M time, but if you did a little bit more efficiently, like he said here, where you use binary search, you can just do it in log n per search. So you have M things times log n, so you end up with M log n. And in general, that's how you do question 3. So to summarize what we did and talk about it, like, and for just more general purposes, the way to tackle these kind of problems is when you first see, look for like certain keywords that really jump out at you. The first thing that I saw was like, it's very, very large. That's what she said. But you just see it's very, very large. That gives you right away like your mental clue should be like, okay, I get it. It's big. We don't want to deal with it as little as possible. To make our complexity better, we want to do operations on smaller files and leave the bigger one alone. So, and it even gave you like another keyword here, a smaller unordered file D. So keeping in mind what's ordered, what's unordered really is helpful. I think it's really helpful, like, draw a little picture like what I did here. People think in different ways, of course, but it's easy for me to visualize things like this where I can like see what I'm doing and see what my goal is. But of course, you can do whatever works for you. And let's see. Understand what's actually happening, because some people also didn't read the question properly and they were thinking that, you know, you're adding file D to file E for some reason, or they think like you removed the elements from F and then put them in E and then put them back into F or something. I don't really know. Some people just misread the question basically. So read the question a few times, make sure you understand the prompt, what they're asking you, and when you do your analysis or how much more efficient something is, you always have to say your big O, and you always have to say your spatial complexity. So let me write this down. Do I have space on any of these files? Okay, so 1, read question. Know what you're doing. 2, look for keywords. Ordered, big, small, etc. 3, when you do your big O's, give complexity compared to the naive solution, and give spatial complexity. So some people actually converted to like a heap, or they did some kind of thing where they made it a linked list and that sort of thing. So if you want to use a linked list, for example, you have to tell me why the linked list is better. So if you use a data structure, why that one? How is it different? Complexity, space required to create it. Like, so for example, if I want to like talk about a linked list is really nice because if you delete something, there's no shifting involved. All you have to do is move the pointer. That's really simple. The downside for a linked list is that you can't search it. You have to manually go through every single thing. So like lookup in a linked list would be on. So that's really expensive, but that's not. But delete/inserts is only like 01. It happens in a constant time versus a linear time. So there are pros and cons for everything. So you have to talk about why your things work, why it's best for this job. So you need to talk about that kind of thing. So a lot of people do like a merge sort. I mean, like use like some kind of like heap or something. They talk about like, oh, I'm just going to heapify it, but they didn't explain why the heap is good, or why you need to convert to a heap, what it costs to convert to the heap, what advantages you get from the heap, that sort of thing. So you need to make sure you talk about that in the future, and do talk about space because very few people talk about that. Um, so space is important. And is there anything else in this question at all? Um, no, I think that's about it. So that's question 3, and there's a mark scheme here. You can see next to everything what like the 1 point was for, like at the expense of n plus m extra space or something. That was worth 1 point. And yeah, so as long as you talk about that sort of thing, you got credit for it. And yeah, so if you have any more questions, you can always message me. But this is in general how I would go about solving the problem and what I was looking for when I created it. So hopefully this was helpful. All right, well, peace.